pleasure to be on campus. This is my first time on Purdue campus, and it's a really beautiful place, so I'm really happy to be here. I'm going to talk about sustainability in the semiconductor manufacturing environment, but before I do, I'm going to give a little introduction about myself and a little bit about the company that I work for, Entegris, and then I'll jump into the sustainability piece. Talk about corporate social responsibility. That's our program. Other companies call it ESG. Or sustainability. We call it corporate social responsibility, and I'll talk about that. And then I'll talk about PFAS. PFAS is a class of materials, per and polyfluoroalkyl substances that are used in semiconductor manufacturing quite extensively, play a really important role, but they're under a lot of scrutiny for a lot of reasons. So we'll jump into that. And then I think we'll have plenty of time for Q&A. So I think, you mentioned a field trip to the West Coast. I think we got to figure out how to do an East Coast version as well, because there's a lot happening on the East Coast as well, and there's a lot happening in the Midwest now as well. So it's great that it's really spreading out beyond Silicon Valley. So let's start with me. So I went to UMass Amherst, the State University of Massachusetts. Graduated back in the 80s. Right after college, I went to work for a company called Shipley. Shipley Company is a maker of photoresists. Photoresists are the materials that are used to pattern semiconductor circuitry on wafers. They're photosensitive materials. Shipley no longer exists. It's now part of DuPont Microelectronics, the big chemical company DuPont, which you've probably heard of. After 6 years at Shipley, I decided that I wanted to extend my education and get a PhD, so I enrolled at the University of Texas in Austin, which is quite different than UMass Amherst. But it was a great experience. I got my degree in organic chemistry. So I'm not an engineer, fessing up front. Any chemical engineers in the crowd today? A few? One? One. We need more chemical engineers. How about material science? Any material science? A couple more. Okay, we need more material scientists as well. Electrical engineers? More, okay. Computer science? Few. Mechanical? Okay. Industrial? No industrial. How about environmental? Not a one? Uh-oh, we definitely need more of them. Okay, so after Texas, I joined IBM at the T.J. Watson Research Center. That's their headquarters for research in upstate New York, about an hour outside New York City. I spent the majority of my career at IBM, 17 years. For the majority of my career, I've worked in lithography. Lithography, again, is the patterning process, the process that transfers what a circuit designer intends to go into the chip into a physical entity on the wafer, right? So it's a projection of light through a patterned mask into a photosensitive material, a photoresist, that then gets washed away and creates a three-dimensional pattern that's etched into a substrate. So I spent the majority of my career working in lithography in different aspects. At IBM, I was the director of the R&D program in lithography and patterning. And then IBM got out of the microelectronics division, transferred it over to Global Foundries, where I worked for 6 years. I went along with it. For the majority of my career, I was in R&D. When I went to Global Foundries, I went into manufacturing. Totally different experience. It was a good experience, but really a very different mindset in manufacturing than R&D. So it was really good to get that different perspective. I later moved into a role where I was doing capacity planning and capital management, capital equipment management. I wanted to get back to my core interest in materials and lithography, so I joined Entegris, which was a company that I knew quite well. I'd worked with for many years. They're a materials company, as I'll show you in just a minute. There I work in the office of the CTO, for the CTO, the Chief Technology Officer. My title is the Senior Director of Engineering. I still work on lithography. We have a lot of products that are related to lithography, so I still work on those. But more and more, I've been spending my time on sustainability. So as a chemist, I made a lot of materials. I made a lot of nasty chemicals. I'm now trying to figure out how I can maybe repent for some of my sins of the past and figure out how we can use less chemicals, safer chemicals, and build sustainability into our new products as we go forward. And that's led me to PFAS, these per and polyfluoroalkyl substances, which we'll talk about later. In my free time, I also work at Tufts. I teach a course at Tufts University in Medford, Massachusetts, on engineering leadership and ethics. It's a lot of fun. And I also collaborated with Professor James Liu at RPI, Rensselaer Polytech Institute in Troy, New York, where we put together a course that's kind of similar to this, where we invite industry leaders from different companies to come and each week talk about a different unit process that's used in semiconductor manufacturing. So we have a few weeks on lithography, a few weeks on etch, a few weeks on deposition, and so on and so forth. And we get people from all the leading companies to come in and speak in that. So it's a little bit similar to this, I think. Okay, so let's talk about Entegris. Has anybody ever heard of Entegris? What do you know about Entegris?
You guys help make systems for
That's right, gases, absolutely. I didn't know that story that Professor shared earlier. That's quite a great story. I'm going to use that in the future. Anybody else know what we do? In addition to making gases and delivery systems and safe storage and delivery of gases, we also make filters that are used to filter gases and filter liquids that are used, purifiers. We make chemicals themselves. We make slurries that are used to polish wafers. We make wet etch formulations that are used to clean wafers. We make deposition precursors that ultimately end up as the dielectrics or the metals that end up in the semiconductor chips. We also make FOUPs. Does anybody know what a FOUP is? What's a FOUP? Yeah, it's a box, right? It's a box that you transport wafers around. When wafers are in the fab, they need to stay really clean. They also need to stay in pristine environments. So we purge our FOUPs with nitrogen so that any materials that outgas get washed away, humidity doesn't come in and complicate the process that you just deposited or have done on the wafer. So we make this wide spectrum of products, all that are used in semiconductor manufacturing. High purity materials, delivery systems, storage systems, filtration and purification systems, FOUPs, FOSBs. FOSBs are the boxes that go in and out of the fab. So a wide range. 95% or about 95% of our revenue comes from the semiconductor industry. The other 5% comes from other areas like other industries like life sciences primarily. We sell not only to chip manufacturers, fabs, both in logic and memory, you know, the household names like TSMC and Intel and Samsung. We also sell to the whole ecosystem. So we sell to other chemical providers. We're a chemical provider. We sell to some of our competition and some of our delivery systems. We also sell to the tool manufacturers, ASML, Lam Research, Tokyo Electron, other companies that maybe you've had speakers from either this semester or in the past. We sell to the entire ecosystem. Well, let me just say, we're based in Billerica, that's how you say that word, Billerica, Massachusetts, which is about 20 miles north of Boston. We're about a $3 billion company with about 8,000 employees that are distributed around the world. I'll show you in just a moment. We're actually the largest material supplier in the industry, and we rank 7th overall. And the top 5 are all the major tool equipment companies that I mentioned earlier. Number 6 is Shidetsu, a Japanese company that provides wafers and photoresists. We're the 7th overall supplier. Not a household name, but really in the fab environment, we play in many different aspects of what it takes to build chips. As I mentioned, we're distributed around the world. We have facilities all over the US, as well as a lot in Asia. We have a few sales distribution sites in Europe and Israel. But you can see, you know, we're coast to coast, north to south, Japan, Korea, China, Taiwan, Singapore, Malaysia. We have a mega factory in Kaohsiung, KSP, Kaohsiung Science Park in southern Taiwan. We have large facilities in Korea. We have a mega factory going up in Colorado Springs that was recently awarded a grant from the CHIPS Act, CHIPS for America Act, to bring more domestic supply chain for the semiconductor industry back to the United States. I work up here in Billerica, that's our headquarters, but you can see we have facilities all around. Tomorrow, actually tonight, I'll be driving up to Aurora, Illinois, right outside Chicago, to visit our facility that makes polishing materials, slurries and pads that are used in polishing. So as I said, we have products that are used throughout the fab. This is a schematic showing a cross-section of a factory Most of the action happens here on what we call the fab floor. This is where all the process tools are, the lithography tools, the polishing tools, the etching tools, et cetera. So we make all the products that I mentioned earlier that are used on the tools that actually fabricate chips. But I like to think of a fab kind of like an iceberg. There's a lot of things that you see, and then there's a lot more down below that you don't see. So there's tremendous amount of infrastructure below the fab floor in what's called the subfab or the facilities level. This is where a lot of the raw materials are provided up to the fab floor. They're stored down below and safely transported up through tubing, pipes, valves, et cetera, pumps. There's also a lot of monitoring systems down there. There's also where the waste goes. So there's a tremendous amount of infrastructure above the fab, actually above and below the fab. As I mentioned, we also supply the entire supply chain upstream from the fab, the wafer growers that make the raw substrates, the chemical and gas manufacturers. What's not listed here is mask manufacturers as well, the tooling manufacturers, research and development facilities, and even after wafers leave the fab, they go to packaging or OSATs, assembly and test facilities, and we make products for that. So we're all throughout the ecosystem up and down. As I mentioned, we have a broad range of products, and we organize ourselves into 3 different divisions. Start with MS, that's Material Solutions. This is all the chemistries that I mentioned, the deposition materials, the pads and slurries used in polishing, gases, formulated cleans. Microcontamination is all the purification and filtration products. And then AMH, Advanced Material Handling, that's the tubing, the drums, the valves, the FOUPs, the FOSBs, everything that's used to ensure that materials, wafers, and masks get moved from point A to point B in a safe and clean manner. The unifying theme of all of it is purity. Purity is absolutely essential in semiconductor manufacturing. Why is purity and cleanliness so important? Anybody have any ideas? Contamination. What if you have contamination, what does that lead to?
Like any tiny sort of imperfection or contamination can lead to like tons of failed chips.
Failed chips. Failed chips are yield.
Yeah.
And yield is revenue, money, right? There's 2 things. Yield, that's the absolute, does a chip work or not? In time 0, when you first test it, is it functional or is it not functional? That's yield. Then there's reliability. What's reliability? It's how long it lasts, and does it last for a long time for its intended life? Think about a chip that's used in an airplane, or in an autonomous vehicle, or in a pacemaker, or something that's mission critical, right? A navigation system, a defense system. You don't want that chip to have a defect that doesn't manifest itself until a year down the road, 5 years down the road, right? These things have to last for a long time. So defectivity is critically important because it affects contamination, it can lead to yield issues, and it can lead to reliability issues. So to do that, we are perpetually looking for ways of reducing contamination. Different types of things that can lead to problems in semiconductor manufacturing include metals, solids, particles, microorganisms, bacteria, etc., things like that, organic materials, trace organic materials. Anything that's not supposed to be there can cause a problem. So we develop solutions to ensure that both the chemicals that we provide or chemicals that come from other suppliers are delivered safely and cleanly. So it's critically important. Why is it so important? Well, we talked about this a little bit, about yield and reliability, but 2 other things are happening. Chips are getting larger, right? Chips are getting larger. A smartphone chip is maybe on the order of 100 square millimeters. Some of these large AI chips that like NVIDIA makes can be 500 square millimeters or more. Why does that make a difference, right? It makes a difference because even for the same amount of defectivity, in this case, in this example, there's 0.1 defect per square centimeter. If you have a small chip with that defect density, you can get about 91% yield, right? The defects are spread out, same number of defects on the wafer, and it affects about 10% of them, 9 or 10%. If you have a much larger die, you're going to be affecting a much larger percentage. So your yield would only be 63%. So that's one factor. The other factor is we're continuously scaling. So as we go through a progression of nodes, we go from the 28 nanometer node to the 22 nanometer node to the 14 nanometer node to the 7 nanometer node, 5 nanometer, 3 nanometer, 2 nanometer. We start to get to the angstrom level. Which defects matter starts to increase. So things that maybe you could live with in the past start to make a difference. So we continuously are raising the bar on both the level of cleanliness that we can tolerate and the size and the nature of the particles and the contaminants that we're trying to control. In fact, we're trying to get down to, in some cases, the parts per quadrillion level. To put this into context, a part per quadrillion is equivalent to a drop of water relative to the amount of water that goes over Niagara Falls in a day. So we're trying to find that one tiny trace metal or particle, finding a drop of water in Niagara Falls over the course of an entire day. Virtually impossible, but we're always up for a good challenge. So we work across a broad variety of solutions for our customers. We're tied at the hip with our customers. As our customers' technology advances, our technology has to advance as well. We're contributing these products that are listed along the bottom for our customer solutions, whether it be in EUV, extreme ultraviolet patterning. This is lithography done at 13.5 nanometer wavelength, really short, super high energy patterning. Stacked devices for memory, gate all-around architectures for logic, backside power delivery, a really innovative new way of delivering power to devices through the backside of the wafer. 3D interconnects, this is stacking of wafers in packaging, or power devices, including like silicon carbide-based devices that are used in vehicles, in EV and other vehicles. As we're doing this, the industry is growing at an incredible rate. So today, we're somewhere around $600 billion industry. By the end of this century, by the end of this decade, excuse me, we're projected to be at a $1 trillion level for an entire industry. So the industry is growing at this incredible rate. It's been projected with the onset of AI that if you extend this out to 2050, we'll be at $5 trillion industry. Enormous. So that comes with tremendous challenges, not just challenges for chip makers and suppliers, it's putting a tremendous strain on the environment. It takes chemicals, takes water, takes energy to make semiconductor chips. Growing at this rate and continuing to do things the way we do them today is no longer sustainable. So we have to do things differently. On the left side, anyone familiar with greenhouse gas emission standards? Scope 1, Scope 2, has anyone ever heard that terminology? No? You've heard a little bit? Yeah. So Scope 1 are the greenhouse gas emissions that come from the operations of what a company makes. So for example, for a chip manufacturer like TSMC or Intel, the manufacturing of chips and the greenhouse gas emissions that come from that manufacturing are their Scope 1. For a company like Entegris, the manufacturer of all the products we make are our Scope 1. So it depends on who you're talking to. Scope 1 has a different definition, but it's the emissions that come from the manufacturing of the products that you produce. Scope 2 emissions are the emissions that come from the energy that's required to run your factories. So if I buy electricity from a power plant that runs coal versus a power plant that's using solar, my Scope 2 emissions are going to be much higher for the former versus the latter. That's Scope 1 and Scope 2, manufacturing and then procured energy. Scope 3, which isn't listed here, is pretty much everything else. It's the transportation of your product from the customer from the source to the customer, it's the transportation of the raw materials, it's the energy used to create the raw materials, it's the use of your product, it's the emissions that are contributed when your product is at its end of use, end of life, et cetera. All of those things, 15 different components. That said, focusing just on scope 1 and scope 2, that's the manufacturing and the procured energy, if we did nothing and maintained this trajectory towards $1 trillion by 2030, you can see that the greenhouse gas emissions would very quickly go off the chart. Now, the good news is there's a renewable energy path that's been defined with this range, with protocols and measures that are being taken that will limit us as an industry from going off the chart, but it still shows about an 8% increase on the current trajectory. What we really need is to reduce that by another 3%, threefold, to get down to something that's more sustainable. It's not just the greenhouse gas emissions, it's the energy that's required. Currently, 10 million kilowatt hours per year are required to run one factory, one mid-sized factory. For a mega factory, like some of the big chip makers are making, that number is easily doubled, tripled, or quadrupled. So huge amounts of energy. Water, about 5 million gallons a day of water are required to run one mid-sized fab. 5 million gallons is about what a city of 150,000 uses in a day. How many people in West Lafayette? A lot less than 150,000, I bet, right? So it's probably several days, maybe a week worth of water usage for the whole city of West Lafayette is used by a factory in one day. Clearly not sustainable. So I don't want to be too depressing because there's good news. People are doing things about it. We need to do more, but there is actions being taken place. For example, people are starting to use renewable energy to reduce their scope 2 emissions. It depends on where you are. It doesn't always make sense to use solar or wind or geothermal in every location, but people are starting to implement these solutions. Likewise, people are starting to really take measures to reduce the water consumption in factories. I think a great example of this is what Intel's done. They have a goal of being net positive by 2030. What that means is they intend to put more clean water back into the environment than they take out. How's that possible? They're going to collect rainwater, they use gray water, they have enormous reclamation systems. I had the opportunity to visit their facility in Portland, Oregon, Hillsboro, Oregon, and it's absolutely amazing what they're doing there. They're able to capture huge amounts of water and reuse it. The other piece of good news is that it's driving increased transparency. So companies put pressure on themselves, their customers put pressure on them to report their energy usage, their water usage, their waste generation. Whether it be in a sustainability report, or corporate social responsibility, some people call it ESG. At Entegris, we call it CSR, corporate social responsibility. And in it, we report on our chemical usage, our water usage, our waste generation, and we talk about new opportunities that we're driving. So I want to share a little bit about that with you today. Got about 10 minutes left, 15? 13, okay. So let me just skip right to it. So we have various pillars. Our sustainability pillar is focused on reducing greenhouse gas emissions, reducing water usage, reducing landfill waste. One example for waste, we are able to reclaim unused materials. Sometimes our customers have a canister of gas or a canister of a precursor. They don't use it all. Rather than draining it and using it, generating hazardous waste with it, we're able to collect it, reprocess it, and reuse it. Similarly, in our factories where we generate parts comprised of plastics, we're able to harvest scrap material that's generated, recycle it, and reuse it. One of our facilities in Yonezawa, Japan, has already reached 99% landfill reduction, meaning that only 1% of their waste is going to a landfill. Everything else is either reprocessed or reused. Another pillar that we have, we call the innovation pillar, is focused on new products. So part of it is related to how much we spend on R&D. We have a goal of reaching 55% of our operating expense budget on R&D by 2030. The other two are related to sustainability. One is related to developing sustainability goals into every new product that we make. It's a lot easier to build sustainability, whether it's use less water, use less electricity, use recycled materials, or design it for reuse or refurbishment, when you're designing a new product from scratch versus trying to change it after it's already been qualified. So our goal is to have 100% of our new products have sustainability in the mindset from day one. The other project that I want to talk about is our end-of-use project, where we're developing circularity or otherwise environmentally friendly end-of-use solutions for all of our products that we can make recommendations to our customers when they're done using our product. Rather than throwing it into a landfill, this is what you can do with it instead. So essentially what we're doing is trying to drive higher value, both from an environmental perspective and provide value to our customers through this end-of-use project, which we call Project Lavoisier. Who knows who Lavoisier was? Anybody? Yes, exactly, right. He was a French chemist. He's considered the father of modern chemistry. He's a gentleman who first identified the conservation of mass. He said, nothing's created, nothing's destroyed, everything is just transformed. So we use that as an inspiration for this project. What we're trying to do is develop increasingly more valuable solutions for our products. So for example, we're reusing wafer handlers after they've been done. We develop a protocol where we can clean them and reach the specification that our customers demand. For our airborne molecular contamination control filters, we're now making them out of recycled materials and building the frames that they can be used multiple times. I talked about precursor reuse, also the materials, the canisters, the shipment, the mode of shipment for these materials are also cleaned and reused. Something as simple as our packaging, the boxes that we ship our products in. Sometimes they're made with plastic. The plastic needs to be disposed of. It can't be recycled sometimes. We switch now to fully recyclable materials. Seems really simple. This thing that looks like a pizza box is what a polishing pad is shipped in. It took about 6 months to requalify that pizza box. So it's never easy, but it's definitely worthwhile. I'm going to switch gears and talk about PFAS in the last few minutes. So PFAS, again, are per- and polyfluoroalkyl substances. It's not one thing. It's not 5 things. It's 30, 40, 50, maybe 100,000 different things. So it's a huge range of chemicals, from CF4, which is a gas that's used in etching, all the way up to super high molecular weight polymers, fluoropolymers, things like Teflon, and everything in between, solids, liquids, and gases. So why are they important? Why are we concerned? Well, I don't think if you have turned on the news or opened a newspaper or looked at a website online, it's hard to avoid news stories about these materials. A subset of these materials, particularly some what's called long chain materials, PFAS and PFOA, they're 8 carbon chain long, have been found to be what's known as PBT, persistent, bioaccumulative, and toxic. Persistent means that once they get into a biological system, like a person, they don't leave. They're not metabolized, right? Your body can't break them down. They're bioaccumulative, meaning they store up, right? You never metabolize them, they never leave your body. And they can be toxic. So this subset of materials have been found to be PBT, persistent, bioaccumulative, and toxic. That's not good, obviously. So as a response, a number of groups and governments have considered putting bans, not just on those that have been shown to be PBTs, but on all 30, 40, 100,000 different materials. This poses a huge issue for the semiconductor industry because, I'm going to skip over that, they're used ubiquitously. They're used in photolithography, again, that's the imaging process. They're used in etching and deposition, wet etch formulations as a surfactant. They're used in tooling and equipment. They're used for all these different applications because they have really unique properties. There's no other materials that are known to man that have the combination of properties. right? So they have properties such as chemical resistance. They're both hydrophobic and lipophobic, meaning that they repel water and they repel organic solvents as well. So they're chemically resistant, they're thermally resistant, they're fire retardant, they are oftentimes have high lubricity, meaning that they have low surface energy, they're slippery, so they can be used for parts that need to slide past each other without degrading, without creating particles. All of these different attributes have made them essential to semiconductor manufacturing. So what are we going to do about it, right? So on one side, there's a subset that are known to be problematic, PBT. On the other side, this trillion-dollar industry is absolutely dependent on it. So we need a collective industry response that takes a really balanced view on this, right? We need to take a risk-based approach and go after those really toxic PBT ones while maintaining safe ways, responsible manufacturing and use of the other materials, right? The ones that we become so dependent on. So the industry has really rallied together from a technical perspective, advocacy perspective, supply chain and R&D. There's different groups working collectively to address these problems. So from a technical perspective, this SIA PFAS consortium, it's an industry trade group that was put together to really illustrate and educate the importance of these materials in the semiconductor industry. Advocacy perspective, we're working with governments to educate them on the importance of it and ensure that they understand that not all PFAS are created equal. From an R&D perspective, we're looking at things like alternatives. It's a long-term endeavor, but we're looking for alternatives. Probably more urgently, we're looking for means of abating or capturing or destroying these materials. They can be destroyed, but it takes some pretty severe technology. Things like electrochemical oxidation are very high temperature processing to destroy them. And then supply chain. We want to make sure that we're identifying risks associated with disruption to the supply chain. By the supply chain, I mean everything upstream that is required to make semiconductor chips. Not just products that companies like Entegris makes, but the products that our suppliers make and the products that their suppliers make, all the way back. We need to identify any risks. So the good news is that we're working together on these collaborative engagements to find a balanced approach, again, a risk-based approach, so we can go after those really problematic ones and maintain responsible use of the others. So with that, I'll point you to a couple of resources that if you have more interest in PFAS, these are great resources to look up. The first is from SEMI, an industry trade group that I'm the co-leader of the PFAS working group for the United States. That has a lot of great information. It's kind of like PFAS 101. On the bottom is the SIA PFAS Consortium's technical papers. They published about 25 different white papers on the uses of these. So it's a very important topic. We need a lot of solutions. We need innovative minds, like the folks in this room, to come up with solutions on how we can control these materials, how we can destroy these materials, how we can find alternatives. And with that, I would happily answer any questions that you have.
So while we're quickly getting set up with the audience microphone, a question that came in that we collected beforehand, which I particularly love, related to the industry presenter we had last week, and it was asking if Entegris uses digital twin type technology and how you might apply it within your business.
So that's a great question, and we are in the process of developing what we call EDIP. It's Entegris Digital Innovation Platform, and it contains aspects of digital twin technology as well as the use of AI and AE, artificial intelligence and automated experimentation, to augment and really accelerate our materials discovery. So one of the most important things in semiconductor manufacturing is a concept we call speed to yield. So when a customer has an innovative project or a challenge, like the ones I mentioned, like gate-all-around or backside power delivery, they're looking to identify solutions to that product and get them into a manufacturing environment qualified as quickly as possible. So we view things like digital twin, AI, and AE as our new tools to help us accelerate that speed to yield.
Thank you. Now over to the floor. Anyone got any questions? We got one at the front.
Oh,
This is kind of a energy related question, but some of the like bigger tech companies, especially those that are powering like GPUs or need a lot of energy for AI models, are kind of looking into buying nuclear power plants and transitioning to that. And I was
I
just
heard
wondering
that.
what your opinion on that was.
well, yeah. I mean, if you had asked me 20 or 30 years ago what I thought of nuclear power, I would probably give you a really different answer than I do today. And it's just because the technology has advanced, and I think there are safer ways of doing nuclear today. But what I think really needs to happen in earnest is a commensurate view on not just how to get more energy, but how to design chips that use less energy, right? So these AI chips they're pigs for energy. They just consume so much energy. So part of sustainability has to be about resource reduction, waste generation reduction. It also has to be about how we design chips that are smarter, that don't require as much energy in the first place.
Yeah, I was just wondering.
Could you wait for the microphone just a sec? Thanks.
Hi. I was, I hadn't really thought of the semiconductor industry as a real, traditionally industrial sort of industry with lots of manufacturing and chemical processes until, taking this course and learning about companies like Entegris. And I was just wondering, with those industries, I think about risk management a lot with the sort of chemicals they produce and their facilities and all of their equipment. I was wondering what your, general thoughts on risk management in the semiconductor industry are and how they might differ from other industries.
Yeah, what I've learned in my 30 plus years in semiconductor, that's an excellent question, by the way. What I've learned is that if there's an unlimited number of ways that things can go wrong, right? So semiconductor manufacturing, for example, for like a 14 nanometer or 12 nanometer node technology, guess how many process steps it takes to do it? A bare wafer comes in the front door, and then a fully processed wafer that has 90% yielding chips goes out the door. How much time and how many steps? Somebody take a guess.
Maybe 1,000 hours,
20 steps, 1,000 hours. What do you think? How many? Couple hundred. It takes about 2,000 steps, and it takes about 3 or 4 months before the wafer comes in and goes out the door. So I don't know how many minutes that is, or hours that is, but it takes about 3 or 4 months. It's an enormously complex process. So anything can go wrong. So the whole game is about risk management, how to minimize risk, whether it's supply chain risk, which I mentioned, right? Your whole factory could go down if that tanker truck of sulfuric acid gets stuck in a snowstorm, right? That's a problem, real life problem, right? Your tools can malfunction, so you have to have all kinds of sensorization around them. Chemical purity, that's where Entegris comes in, right? We have to make sure that that chemical is clean every day, every single time, no exceptions. If you have an excursion, that's what it's called when something goes wrong, it can very quickly get out of control and lead to huge yield loss. And in some cases, it could lead to a safety issue as well. So one of the things that we take pride in is safe delivery. I mentioned it a couple times. Yeah, purity is super important, but safety is of the utmost important. So a lot of the products that we make is about how to handle very nasty, for lack of a better word, chemicals in a safe manner. Great question.
You mentioned earlier about digital twin technology being used for the engineering and design process. As that gets used more, is there any kind of security concerns that you have from a supply chain perspective that might be of interest when you guys are looking at this kind of stuff?
That's a really good question. The question was about security concerns related to digital twin technology and the use of it. It's a really good question, and it's one that everyone's kind of grappling with now. Yes, it's a super big concern. And one of the things that we're interested in is there's a few companies out there, we're a customer of these types of companies, working with companies that allow for the anonymized input of data, our data, for example, from our factories about different lots of material, different raw material suppliers, this batch, that batch, all that information, and coupling it with anonymized data from a customer, right? So a chip manufacturer, for example, and their yield data, their process conditions, things that they want to keep secret from us, things we want to keep secret from them, but putting them together in an anonymized way, in a secure, anonymized way, and be able to build correlations from those comparisons using advanced machine learning or AI. And then once you see the anonymized results, it might be like parameter X and parameter Z correlate with your variables A, B, and C. Then you can have the conversation, do you want to take it a step further and start getting into the details? But there's a lot of thought going into how to do this in a secure, safe way. It's a good question. Really hot topic at the moment.
Hi, thank you, Dr. Medeiros, for coming today. Your discussion was great. I just wanted to ask about what has been more of a challenge for like a bottleneck for reaching sustainability? Has it been recycling these materials, or has it been more of capturing these materials before they go out to pollute the environment?
Yeah, it's the most unsatisfying answer that you'll ever hear. It depends. It depends on the product. It depends on the chemical. Sometimes it depends on the location and like the regulations. It also depends on the willingness of the customer to engage, right? So different customers have different levels of intensity around their sustainability goals. Some are really eager to engage. Others are like, well, that's not my top priority at the moment. So, sometimes even the technical solution is not the biggest challenge. Sometimes, every time we develop a solution for a sustainability challenge, you have to develop, obviously, the technical solution. But then you also have to weigh it against what resources does it take to implement that solution, right? For example, if it's a recycling solution, does it take more processing, more energy, more water usage to do the recycling than to get the virgin material in the first place? Or does it cost more? There's always the cost component as well. So sometimes the technical solution is the easiest part, right? It's getting the attention from the customer, getting the qualification, because generally change requires requalification. And guess what? That costs money and time. So people have to prioritize it. It's making sure that the solution doesn't cause more problems than it's worth. And of course, always the financial aspect. A lot to worry about. And every situation is different. Every product is different, every chemical is different, and like I said, sometimes every geography is different because of regulations.
I think we have time for one more question, or I have some on the list. Okay, a careers-related question. Would Entegris engineers need to have a heavier background in chemical engineering, or do other kinds of engineering play a large role?
Yeah.
And in Entegris's world, what fields are the most valuable to you?
Yeah. So the short answer is no, it's not required that you have a chemical engineering degree or a chemistry degree. We hire chemists, we hire chemical engineers, mechanical engineers, industrial engineers. Increasingly, we're looking for people that understand semiconductor processing end to end, like integrators, like EE type folks that would really understand the circuitry, because it's important for a company like Entegris not only to know our business, we need to know our customers' business. So we need to know why they need our products, what their pain points are, and how we can address them. So we need all of the above: industrial, mechanical, EE, chemistry, physics, math. We need all of them. And increasingly, we also need CS and IT type folks.
Anyone want to squeeze a last comment in? Well, thank you very much.
Thank you. It's been my pleasure. Really appreciate it. Thank you all.